Bismillahirrahmanirrahim. So today we will be having our sixth lecture, and we will be discussing more logic functions, and we will be studying NAND, NOR, XOR, and XNOR, right? So these are the bullets which we will be covering in today's lecture, right? You can have two input logic gates, NAND, NOR, XOR, and we can extend to more than two. You can have 3 inputs, 4, 5, and so on and so forth. And then the conversion between sum of the products and NANDs. You can convert NANDs to sum of the products and sum of the products to NANDs, right? So then we will be having conversion between sum of the products and NOR, right, and NORs to sum of the products, because those are considered, NAND and NOR, they are considered as universal gates. You can have all the Boolean functions by using NAND, and you can also have all the functions and or not by using NOR as well, right? And then we will be discussing positive and negative logic, but we will be emphasizing on positive logic during our lectures, right? So if we have n variables, right, and so you have to represent truth table by using those n variables. So how many truth tables you normally have? So we have the expression, general expression mentioning 2 raised to power 2, right, and n is the number of variables. So if you have 2 variables, so 2 raised to power 2 and then 2, so we will be having 16 different truth tables, right? And this is the table mentioning how many different truth tables we can have whenever we have 2 variables, right? So you can have operation name, and then this is the logical NOR, then we have the negation, right, NAND, right? So all these are different operations. So we will be having 16 different truth tables, right? And this is the NAND gate. This is the symbolic representation of NAND gate. The only difference is this bubble. So this is, if we remove this bubble, this is the AND gate, right? So it has several interesting implementations, like you can have a NOT gate by using NAND, and you can have an AND operation by using NAND, and we can also implement OR operation by using the NAND. So this is the truth table, right? So this is the complement of the AND operation, like if due to this bubble, right? If you have AND, we will be having a 0 over here, a 0 over here, a 0 over here, and 1 over here. So if you complement this, 0, 1, 0, 1, 0, 1, 1, 0, right? So this NAND is 0 sensitive. Whenever one of the input has 0, it will produce a 1. So this is a 0 sensitive gate. You can also explain like that. Whenever we have a 0 on any one of the inputs, the output will be high or 1, right? Okay. So there are different properties or characteristics of this NAND gate, because this is considered to be a universal gate. As I have mentioned, that you can implement NOT operation by using this NAND, you can implement the OR operation by using the NAND, and you can have the AND operation by implementing or by using this NAND gate, right? So these are the basic functions of Boolean algebra, right? So you can say that this gate is a primitive gate, or it has a complete functionality because we can implement all the basic Boolean functions and or not, right? So if you look at this, what we have did over here, we have this input A, this is A, this is A. So what we will be having over here, right? We will be having A dot A, right, whole complement due to this bubble, right? So that is equal to A complement. Break the line, change the sign, we are changing dot with plus, and we are having this, right? So that is equal to A bar, right? So this is the NOT operation. You have input A and we got the A complement, but this is the NAND gate. So you have used the NAND gate and you have implemented the NOT operation, right? So this is the NOT gate. And what is this, right? If you look at this, right, so this is the NAND gate, right, and this is what, right, this is the NOT gate. So this bubble will be cancelled out with this bubble and you are left with AND operation only, right? Because we normally say that the double complements, they cancel each other. So let's have the expression, proper expression. So if you have A dot B and then we have the double complement, right, due to this NOT. So what we will be having, right, so break the line and change the sign, plus break the line, change the sign, but we have this bar, right? And then what we can have, we can break the line, change the sign, so we will have the double bars, right? So those double bars, they will be cancelled and we are left with A dot B, right? So we got A dot B. So this is what, this is the AND gate, right? So this is what, so this is the NOT, right? If you look at this, this is the same and this is also the same. So we will get A bar, right, and this is the B bar because this is the NOT operation. A will be complemented and B will be complemented as well, and we have A bar dot B bar and whole bar, right? And what we will be having here, right, so we will be having break the line, change the sign, so we will be replacing this with this, right? And we are left with A plus B, right? So this is the OR operation. So you use NAND gate and you can implement NOT operation, you can implement the AND operation, you have implemented the OR operation as well. So this shows the universality of this NAND gate, right? This is the OR operation, and you can also cascade NAND gates, right? If you have a 3-input NAND gate, right? So this is the cascading of NAND gates, right? So you can have 4-input NAND gate and so on and so forth. So this is a sort of cascading. You have A, B, C. This shows the complement, and then D, E. This is also complemented, and then this gate will this and this complement, right? So you can change the sign and you can break the line, double bar, and double bar will be cancelled out and we will be left with ABC plus DE. So you can also have cascading of NAND gates, right? So this is the NAND gate implementation of NOT and OR operation, but we have mentioned over here the axioms of Boolean algebra. So here we have used idempotency, like you have shortened, right? You have joined or connected the two inputs of the AND gate, or this is X, so we have X dot X, right? And you have placed, so we will be using plus X bar, right? So X bar plus X bar is equal to X bar. So this is the NOT operation, but we have used idempotency property. So here we have implemented the AND operation, but what we have did over here, we have used the idempotency and involution property. Double bar are cancelled, right? And we are left with XY, which is the AND operation or AND functionality, right? So this is the OR implementation, right? So you can see that we have used more axioms while implementing the OR operation. So here we have X dot X, right? Whole bar or whole complement, Y dot Y whole complement, right? So X dot, because X dot X X, right? And Y dot Y is equal to Y. So the complement remains the same, and then we have implemented this complement, right? So break the line, change the sign, plus sign, double bar, they will cancel out, right? So here you have used idempotency, right? When you have replaced X dot X with X, right? And then we have used the DeMorgan's law. You have implemented, or you have broken this line and you have changed the sign, and then we have used the involution property, like double bars are cancelled out, so we are left with X plus Y, and this is the OR operation. So we have X as input, Y as input, and the output of this whole block, right, is an OR operation. So this is the NAND gate and the corresponding implementation of Boolean laws, right? So this is the NOR gate, right? So we have different functionalities. We can also implement NOT operation, OR operation, and the intersection or AND operation by using these NOR gates, right? So this is the truth table. You can see we have two inputs, and if you keep in mind the OR operation, whenever we have we have a 1 over here, right? 1 over here and 1 over here, right? So this is 1, right? So if you complement this 0 1 1 0 1 0 and 1, so this NOR gate is 1 sensitive. You can say that whenever we have a 1, we have 0 as output, right? If any one of the input is 1, we will get the 0. So here we have B as 1, here A as 1, we got the 0, and these here we have both A and B 1, and we got the 0, right? So this is also a sort of universal gate. You can have all the functions using, right? So this is the NOT operation, right? So you have, for example, let me use the pen. So you have A, right? plus a whole complement due to this bubble. So we are break the line and change the sign, right? So here we have dot a, right? So a bar dot a bar will be a bar. So this is the complement or not operation or complement operation, right? So this is the AND operation. You can have like a plus b complement, and this portion, right, is the NOT operation. So we will place another complement, right? So this is equal to, we will solve the inner complement, break the line, change the sign. So here we have NOT in the complement, so whole complement, and then break the line, change the sign. So we are left with double bar, here again double bar, right, double bar. So the double bars will be cancelled out and we are left with a plus b. So this is the OR operation, right? This is the AND operation, right? So here you have for example, this is the NOT operation, so we have a bar and this is the b bar. So here we have a bar plus b bar, right, whole bar, and we will break the line and change the sign. So we will left with, right, so we have a, right, dot b with double complements, right? So those double complements, they will cancel each other and we are left with a dot b, right? So this is the AND implementation using NOR gates, right? AND implementation. So this is the implementation with the axioms. So here we have used the idempotency, right? So here you have used the idempotency, right? And here you have first idempotency, then you have implemented the DeMorgan's law, and you have solved this outer complement, and you have broken this complement, and you have changed the sign. Then we have used the involution property, double complements, they cancel each other, right? And we have used involution property over here. So here you have the AND operation, and here we have the OR operation. So you have the NOR, and this is the NOT gate. So x plus y bar, and after the double bar they will cancel out. So idempotency, right? So x plus y bar plus x plus y bar. So this is, if you say that this x plus y bar is a, then plus a, right? So we will get a, which is x plus y bar, and then whole bar, and then these bars, they will be cancelled out by using the involution property, right? So we have shown the implementation of NOR with Boolean axioms, right? So this is the XOR, another right, or it is pronounced exclusive or you can say XOR. So this is the truth table, right? 0 0 0 0 1 1 1 0, right? So you can represent this XOR operation by this symbol, right? So whenever one of the inputs, either A or B, is high but not the both, you can see whenever we have one input high, A is high, and here B is high, and here A is high, we have the high output, but not the both. When both of the inputs are high, we got the 0, right? So this is the important property of this new Boolean function, Boolean logic, XOR, right? So we can also have exclusive NOR, right? XNOR, so you can complement or you can invert the output. So if you have XOR, simple XOR, here whenever we have 1, either A or B, we will get 1, and when both the inputs are high, we will be having a 0, right? So you can complement this 0 1 1 0 1 0 0 1, right? So this is the XNOR, right? So this is the symbol to represent XNOR. We have a dot here, and in the XNOR we have the plus sign inside the circle, right? So this is the difference, right? So this so you can also implement the NAND, the XOR functionality by using NAND, right? So you can because this is the Boolean expression of XOR logic, A bar B plus A B bar, right? And whenever you have to convert, or you have to implement the functionality with another logic, Boolean logic, what normally you do, you take the double complement. So you will take the double complement on both sides, so these double complements, they will cancel out, and we will operate these double complements. So if I implement the inner complement, right, so break the line, change the sign, so I am solving this inner line, right? So we have this, right? So this is the NAND implementation. You can see that we have NAND. So we have A, so here we have B, right, state, and here we have A bar, right? So here we have A, right, and this is the B bar, right? And then what we have here, over here, we have A dot B bar, right? So here we have A bar dot B. So what you will be having, right, A B bar, right? So they will be having another complement which I have not placed here, right? Right, so this is the A bar B, right? So whole complement, and so this is the same expression which we have over here. So this is the NAND implementation of XOR operation, right? So this is the XOR operation, simple XOR operation, if we solve the double complement straight away, right? So this is something. You can also have the XOR implementation by using NAND, right? So this is the XNOR implementation. So what you did over here, you have this is the same functionality, right? And but we have over here, so we have the A bar B plus A B bar, right? But using NAND, right? And what you did over here, which is different from the previous slide, we have a bar over here due to this NOT gate, right? So this is the symbol, right? You can, this bubble indicates inversion, right? You can have bubble with this, or you can also have another representation, symbolic representation of this NOR gate, right? So this is the truth table, this is the OR, this is the NOR. And the only objective is to show you different representation of NOR gate, right? These are DeMorgan's laws, our old friends, right? We will be keeping them always with us. So this is the example how you simplify whenever you have complements, right? So this is another example. You can solve it by yourself. You have a complement, right? Because we have a NAND, right? So this C is already complemented, and then we have the final expression A dot B dot C bar and whole bar due to this bubble. And you can solve this. You can break the line, change the sign, but here the difference is that we have three variables, so we will be having three little bars over the three variables, A bar plus B bar plus C double bar. So this double bar will cancel out and we are left with A bar plus B bar plus C, right? So this is the combinational logic, right? And you can combine different logics, like here what we try to show here, that we have the AND operation and we have the OR operation, right? So these are the NAND implementations, right? We have started from here, right? So this is the AND, right? And this is another AND, right? AB and CD, right? So you replaced this NAND, right, with this OR but with bubbles, right? So this and this, they are equal to each other, so you can have a solution, right, if you have complemented inputs, right? So we have a XOR here and you have complemented inputs over here, so we have A bar plus B bar. But if you have the NAND, right, so what we will be getting, A dot B whole bar, so we will be getting A, change the sign, break the line, so we will put a plus here and this. So this and this, they are the same. So what we did over here, we have replaced this NAND gate with this OR gate but with the bubbles, or we can say inverters. So these are the same, but as you know, if after the replacement you look, we have two bubbles and each bubble represents a complement. So if you have two complements, right, so what normally we do, we cancel those complements. So these bubbles, they will cancel out and you are left with this circuit or with this implementation. So this is a sort of simple example of combinational logic. So here we have AND operation, and OR operation. So we have A, B, C, D, and they are ORed, or they are added by this OR gate, right? So as I've mentioned, you can have inverter by using this NAND gate, right? So here we have the NAND gate and this is equal to this converter. So here we have the AND implementation by using NAND, right? And here we have the OR implementation by using the NAND gate. So one of the difference between the NOR and NAND implementation is due to the fact that NAND implementation, they are more native to the manufacturing material. You can manufacture easily, or they contain some inherited properties, right? So in the industry, NAND implementation are more frequent than NOR implementations, right? So this is the NOR implementation, right? So you can have the inverter by using NOR gate. You can also have the OR operation by using NOR gate, and you can also have the AND implementation using the NOR gate, right? So this is the example, right, mentioning mentioning different implementations. So you can see different numbers over here, right? So these are the chips, integrated chips, right? So you can see different pins. So we have 14 pins over here, and we also have 14 pins over here. So we normally have a ground, and this is the supply voltage. We apply the supply voltage at pin 14. So we have a ground here, we have a ground here. So these are the different implementation of AND, NAND, and OR, and these are the numbers regarding those different logical functions or Boolean function implementations, right? So this is the interpretation of different symbolic representation of the NAND gates. One implementation is that we can have a bubble at the output of the AND gate, and we can have the NAND implementation. But you can also have an OR gate, and you can place two bubbles at its inputs. If you have two inputs, so you also have, right? So this is also the NAND implementation, right? So here you can see we have the same expression, a dot b whole bar, a dot b whole bar. So this is one symbolic representation. Here we have the bubble at the output, and here we have the bubble at the input, but we have changed the gate. We have OR gate over here, right? So the output goes low only when all inputs are high, right? So output is high when any input is low, right? So this is the difference between those two implementations, right? So this is the OR interpretation, symbolic interpretation. You can have this symbolic representation, right? So we have this OR operation, or what you can have a NAND gate with two inverted inputs. So we have two bubbles over here, right? And we have the same expression, same output, A ORed with B, and over here A ORed with B. But the difference is that output goes high when any input is high, right? And the output goes low when all inputs are low, right? So you can guess the difference between those two different symbolic interpretations, right? So these are the alternative representations, right? So over here we have an AND gate, but you can replace this AND gate accordingly. But we have OR gate, or you can say NOR gate, right? If you include this bubble with this NOR, then the two inputs, they are inverted, right? So we have the same expressions, right? And here we have the OR operation, and we can replace this with the NAND, but with inverted inputs, right? So these two outputs are the same, and here we have the NAND implementation, but we have OR gate, but the inputs are complemented. So these bubbles, they are mentioning the inversion or complementing the input, right? So you have actually you are handling the complement externally, right? So the gate is OR, but the inputs are complemented beforehand, right? So here we have the NOR implementation, right? And we can replace this with AND gate but with complemented inputs. So here again you are handling the inversion externally. So this is the inverter. So you can have the bubble at the output, right? Or you can have the bubble at the input, right? So those different representations you can use them interchangeably. If you have this and you feel that you are comfortable with this, so or your design requires, or your in another case if you want to implement an OR, so you can replace this with this, right? As in one of the previous slides we have mentioned, like we have replaced this NAND gate with this bubbled OR gate, right? So these bubbles, they cancel each other, right? And we have this simple implementation where we have AND OR implementation, simple AND OR implementation. So these sort of interpretations, they are important when you are emphasizing on a certain sort of implementation, right? So you can replace this NAND with this OR gate but with inverted inputs, right? So here as I have mentioned at the start of my lecture that we normally have a positive logic and a negative logic, right? And what that positive logic and that negative logic means, I will be explaining over here. And as I have mentioned before, that we will be emphasizing or focusing on positive logic mostly throughout this course. So here if we have an AND operation, right, this is the output, right? So we have a low, low. So normally when we have a NAND operation, so we AND operation, we get low, low, high, we get the low. Any one of the input is low, we get the low, and high, low. Any one of the input is low, we get the output low. When both inputs are high, we get the high, right? So this is the normal gate behavior when we talk about the AND operation. So this is the positive logic. You represent low with 0, right? And whenever you have a high, you represent this high with 1, right? So we have a high, low, 1, 0, high, high, 1, 1, and this is the normal AND operation. So we have a 0, 0, 0, and 1. But when we want to have a negative logic, we represent the low with 1 and high with 0. So you can see that low, low we represent 1, 1, right? And when we have low, high, right, 1, 1, right, 1, 0, low is represented by 1 and high is represented by 0, right? So here we have a high, low, high is represented by 0 and low is represented by 1, right? So here we have high, high, both inputs are high, so we are using negative logic, so that's why we will represent those high with 0, 0, right? This is the OR operation, so you can see we have 1, 1, 1 and 0. But remember, we are using negative logic over here, but here we are using positive logic, right? So this is the difference, right? So this slide I have added so that we can have an idea, because we have to live with this slide whenever we talk about the simplification or conversion, right? So these are the axioms, and I have added the graphical representation of DeMorgan's law, right? So we have the commutative law, right? We can commute, right? And we have the associative law over here. You can associate y with z, or you can associate x with y, and these are the same representation, right? So this is the association when we have the AND operation, and this is the association when we have the OR operation, right? And this is the distributive law, right? This is the distribution over addition, and this is the distribution over multiplication, and these are the consensus theorems. So this is the graphical representation of DeMorgan's law. They are very, very important regarding the simplification. And we have x dot y whole bar, and if you remove this bar, you will be getting x bar, right, and y bar, but we have to change the sign because we have broken the line. So this is the plus. So you can see that we have handled those complements externally, right? This is the x bar and this is the y bar, right? And then we have x plus y bar, right? So what you can have bubbles at the input of an OR gate. So these bubbles will invert the input, so x bar plus y bar, right? So this is the second Boolean law. We have a NOR gate, x plus y whole bar, right? So what we have a bar over here, so that is equal to x bar y bar. If you talk about the second law, we have a NOR gate over here, and you have x plus y whole bar, right? So you have to break the line, and you will be changing the sign. So this sign will be replaced by dot, addition will be replaced by multiplication, and we have the bars on the individual variables, so x bar dot y bar. So this is the x bar, right, and this is the y bar, and we will be having x bar dot y bar, right? So what you can have those bars externally. You can handle those bars externally, so you can put bubbles at the input of an AND gate. So this will be x bar and dot y bar. So this is the representation. Then we have those consensus theorems, right? This is very important property which normally we have to use whenever we are simplifying a Boolean expression, right? X plus x bar y is equal to x plus y, right? And this is the another way of having this consensus theorem, x bar plus xy is equal to x bar plus y, right? And this is the x plus x bar y bar, so x plus y bar, right? And these are the Boolean laws, right? So this is if you think about switching, so you can replace, or you can have the equivalent switching circuit against each Boolean axiom. So here we have a plus 1, right? So and you can construct a circuit, switching circuit. So a is always so we have a over here. So this one represents that this switch will always be closed, right? So you can see that irrespective of a is closed or open, because when we talk about switches, what we can do, we can open the switch or we can close the switch, right? So here, if in either case either a is open, we have a 1 over here, and or a is closed, so we have a 1 over here, because this switch is closed forever, right? So this is the annulment property, right? So here we have the identity property, right? So here a plus 0, so this switch now is closed, is open forever, right? So we will be having whatever a is. If a is open, we will be getting 0 over here. If A is closed, we will getting the 1 here. So in case of A is open, we will have a 0. In case A is closed, we will have a 1. So we will get the A, whatever A is. If A is open, we will have 0, and A is closed, we have a 1, right? So this is the identity element, but the operation is changed now. We have the AND operation rather than addition operation or OR operation, right? So 1 is the identity element if you talk about the AND operation. So 0 is the identity element if you talk about the addition operation or OR operation, right? So here you can see that we have placed the switches in series rather than in parallel. So we have A, this switch is always closed, so whatever A is, right? So you can see if A is 0, right, mean switch is open, so we will be getting a 0, right? No current will pass through. And if A is 1, it means switch is closed, we will be getting a 1. So 1 is the identity element for the AND operations. And then we have the annulment. So here we have 1 as annulment, right? If we have the OR operation, so if we have the 0, so A dot 0 is always 0 because this switch is always open, right? So but they are cascaded in series, right? Rather than here we have parallel implementation, right? So then if we have A plus A, so you can a switch like this. Here we have A, or here we have A. They are placed in parallel. So this is the idempotent property which normally we have whenever we have same Boolean expression, we can replace it by a single Boolean expression, and the operation is OR. So either A here, either this switch or this switch, we will be getting A over here, right, irrespective of this or this, right? And then this is the idempotent regarding the AND operation. So here A dot A is equal to A, so the switches are cascaded in series. So these are the important properties, right? And then you can have a NOT, right, double negation. Then we have the complement, right? So here we have A, right? So its complement, if A is open, its complement, the switch will be closed, right? If you take the A as closed, then this A complement will represent the open switch. So in both cases we have 1, right? If this is open, this has to be closed, and this is closed, this has to be open. So A plus A bar will always be getting a 1, right? So this is the complement. So in case of so this is the OR operation. In case of AND operation, right, we have A dot A bar is equal to 0. So now we have cascaded the A and its complement in series, and we will get a 0, right? If A is open, so A bar will be closed, and then if A is closed, A bar will be open. So the current will not flow, or we will not have the output, so we will get a 0, right? And then when you have two variables, A and B, so we design them as two different switches. This is the A switch and this is the B switches, right? So you can have A plus B, right? A or B, or you can say B or A. So you can commute them. So this is the commutative property. And similarly, if you cascaded those different switches in series, so you can have the same. So A and B, or you can place B here, right, or A here, so they have the same impact. So this is the commutative property regarding the AND operation, right? So these are the DeMorgan's law. So now what I want to repeat, because this is very important, right? So this is the NOR implementation, right? And we will be implementing the basic Boolean operations, not, and, or, right? But what we will be pointing out over here, that we will be mentioning the different Boolean axioms or laws that has to be used. So here we have used idempotency. You can say that we have x plus x, right? So x plus x, we can place it with a single x. So this is the idempotency property, right? And then we have the AND implementation using NOR gate, right? So here we have the idempotency property. So if you take this as A and this is as B, so x plus x is equal to, so this has to be x, right? So there is a mistake. So this has to be x. So x plus y, no, it's this is y. So x plus x, we will left with a single variable, and then y plus 5 we will. So now we will be using those different Boolean axioms when we want to have the basic Boolean logic implementation while using the NOR gate, right? So, but the difference is that now we will be mentioning the axioms, that what sort of axiom we will be using when we are converting those NOR operations to NOT, AND, and OR. So here, if you look, we have x plus x, right? So you can say that we have variable, same variable, and the operation is OR, so we can replace this with a single variable. So we have x bar, and we have used idempotency property, right? And then whenever we want AND implementation, but by using the NOR gate, so you can see we have x plus x, so we can have a single variable over here, and then we have y plus 5, we have a single y, right? So the complements will be there, right? X complement plus y complement, and then we have the whole complement. So whenever we have replaced the two variables with a single variable, we have used this idempotent property. Then we have used the same principle, DeMorgan's principle, change the line, change the sign, and break the line. So, or you can say break the line and change the sign. So, right. So this is the DeMorgan's law. So here you can see that we have the double complement, and the double complement, they cancel each other, and whenever we talk about the cancellation of double complement, we use the involution property. So here we have three different axioms or laws, right? And now we can have the OR implementation. So simply what you can have, if you think about this implementation from the circuit point of view, circuit design point of view, right? So here we have the OR implementation using NOR gates. So if you think from the circuit design point of view, you can have a look that we have a bubble over here, and this portion is also representing a bubble. So those two bubbles or those two complements, they will cancel each other, but we have to talk about laws. So x plus y bar, right? So then we have due to this implementation, we will add the same x plus y complement, and then due to this bubble we have the whole complement, right? So here we have the similar expression, right? So we use the idempotency, so we are left with the single variable, right? So x plus y or single expression, right? And then the double complement will cancel each other, so we have the involution property over here. And then we have the NAND implementation, but we will be focusing on the laws. So here we have used the idempotency like x dot x whole complement, so you can replace this with a single variable, right? And you can have the AND implementation by using NAND, but again we have to mention the laws. So you can have x dot y complement, then x dot y complement because of this. So x dot y complement, and then we have the x dot y complement, right? Because we have two inputs. So then we can use idempotency, and we are left with this x dot y complement and whole complement, and we will cancel out the complements by using the involution property. So here the OR implementation using NAND, right? So this is the NOT. X will be inverted to represent the complement, and y is also inverted to represent the complement of that variable. Then we have x plus y. So here x dot x, right? Because we have right. So x dot x complement, right? So y dot y complement, whole complement, right? So what we have used idempotency over here, right? So you can replace this with a single variable x bar, then y bar, then this complement will be broken, and we have to change the sign. Break the line, change the sign, so we will be using the DeMorgan's law. So then these double complements, they will cancel each other, and we will be using the involution property over here, right? So that's all for today's lecture. So today we have new Boolean functions, NAND, NOR, XOR, XOR, and we also studied how we can implement the basic Boolean functions that are AND or NOT by using NAND, and then by using NOR, right? And then we also implemented XOR function, Boolean function, by using NAND, and then XNOR by using the NAND function, right? And we also discussed about the combinations, like how we can use their combinations, like if you want to have AND and OR combinations, so how you normally construct those different combinations, right? And finally we have discussed those NAND and NOR implementations, but we have mentioned different Boolean laws or axioms, right? So my recommendation to you is you should read the text as much as you can in order to have more clear understanding. So most of the slides I normally design, they are from your main textbooks. So if you will read the textbook, you will find a similarity between my stuff and the textbook which we have chosen for the for this course, right? So that's all for today's lecture. So मेरी तरफ से अल्लाह हाफिज़, अपना, अपने दोस्तों का, अपने गिरदोनवा का और अपने घर वालों का ख्याल रखिएगा। अस्सलाम वालेकुम।